working. Okay, so during the last lecture we have been learning about pointers and generally how larger memory blocks are handled in C and C++. And today we will take a look on a mechanism of C which is quite useful with regard to creating very basic type of objects, so-called structures. So let's create a new project. And the idea behind structures is basically to be able to refer to a block of memory which can contain in turn variables of different defined types internally, and so that you have one handler, one object you can pass to some function or just pass around inside of your function, and then from it refer to further elements that it contains. So such objects can be created with the struct keyword. Let's call it myStruct, and let's give it a few member variables. For example, int var a and int64 var b char var c short var d, again a char maybe, char var e. Okay, for the starters that should be good enough. And the idea is that such an object will simply just contain those variables one after the other in the memory, and then the whole thing can be referred like to a variable. So we can create myStruct vars, and this thing then can behaves like a single variable. You can copy it, so it's quite nice to work with. So a simple example, if you want to access a variable, let's say you want to set the first one, so which we just use the dot operator, our structure variable name dot, let's set variable a to a value, and if you want to read a value, we do the same, we just use the dot operation. When this thing would be a pointer, so we can also create a pointer to a structure. Just use the asterisk operator, p var s equals reference var s. So this behaves like normal variable set pointers that we had before, but there is an interesting difference. While here we access member variables with a dot, if we have a pointer, we have two ways how we can access a member variable. First is, of course, we dereference it like with a normal variable, and then we use the dot operator. But since this is ugly and takes more time to type, there is also the arrow operator, which can be used on pointers which point to non-trivial types, and it pretty much does the exact same thing. So these two lines are fully equivalent, they're just written differently. And the letter type is how you usually write it, and it is much more convenient. Now, as you remember, we can just initialize variables. The question might be with a structure how to do this, since a structure has more than one variable internally, and you can do it like this, and then you just specify the values for the individual entries. So let's say 1, 2, 3, 4, 5, and that's it. So basically you do it the same way like for an array, just that instead of all elements being of the same type and the same size, the elements here can be of different types in whatever order you want. Which brings us to a property of arrays, of structures, which might not necessarily be initially intuitive, which we'll see in a second. So let's just start by just writing down how large each of our fields is in bytes. So first we have 4 bytes, then we have 8 bytes, then we have 1 byte, then we have 2 bytes, and then we have 1 byte again. So if we add everything together, actually let's write it like this. That looks that looks nicer. We get 4, 12, 13, 16 if I did not miscount it. And now let's see if this in this case is true. Short hint, it won't be. Const int let's do it here. Browse size. You remember the size of operator. You need the brackets, which gives us basically the size of whatever we feed it, and we get not 16, we get 24. How is this? Why is this? Well, most CPUs now, not just nowadays, but pretty much since they started to be at least remotely powerful, use caching. They use a lot of caching because access to RAM is slow. Nowadays, not as slow as in the last century, but in comparison to the speed cache memory or registers in a CPU can be accessed, it's orders of magnitude slower. And when caching, you of course want to somehow optimize. And what CPUs do is they read data in chunks, and usually they also the performance of the cache and the utilization of the cache is contingent on cache alignment. So if when you read something to the cache, it starts at the right offset, or if you then need to within the cache then pick out at some offset, or worst case, if you want to read something and it doesn't fit into one cache line, but you need then to use 2 cache lines, so such things kill performance, and therefore compilers by default, when you create arrays, or generally when you create variables on the stack as well, what they will do is they will try to align the data inside your structures in a particular way. So they will not change the order, but they might add empty unused spaces, and this is what happens here. So our structure here, as we remember, this was 24. So we are actually missing 8 bytes somewhere, and those bytes are located. One is here, and the other one we have to look up. I think it should be there, but it can be checked. So the idea is basically that if we access this 64-bit variable, that we do it on a address which is a multiple of 8, basically. This gives us a nice memory alignment for a efficient access. And while on x86 CPUs, this alignment is a purely performance-related thing. The CPUs can handle working with pretty much any indices. When working with ARM instructions with ARM CPUs, memory alignment is to some extent enforced. So you cannot just jump to an arbitrary address, or you cannot load something into a register from an arbitrary address just like this. Realistically, of course, if you're writing something in C and then you want to create a structure, there are ways to create them with different alignment, and you want to access some random address, this will be made possible transparently, but internally the compiler might then create more code, because we'll need to like load to chunks, then shift the data inside, and then only load it to where you want it to be. So it will be also less performant, but unlike x86 CPUs, where it will be the same amount of instructions, it just might run slower. Here it will actually be more instructions, and it will be apparent from the code that it is less performant. So let's see how we can find out where these variables live inside our address, inside our variable. So var s p var a, and we want an address, so let's go with f with asterisk. So obviously the first variable will be just living at the address of our var s. So this, when we see what it gives, that it will not give us a value. Let's go with asterisk. Since I showed you a preprocessor macros in the last lecture, we can actually utilize this quite nicely. So define get field offset, get field offset, and let's say we want the name and of a given type. We'll need to fill this with something later, but let's first const int s that is how we will want to use it. Then we can just provide any variable. Just directly provide, for example, the var b, since this is what we need, and then let's see how we can do it. So what we can do to obtain the exact offset is to use pointer arithmetic. So from our lecture about arrays, you might remember that if you have an array, or generally you have some memory, you can advance to the next or previous elements using mathematical operations on the pointer variables. And here, in principle, we can exploit this mechanism to get the exact addresses of something. So let's see how we would do that. So we know the type, so we say type asterisk, and we cast let's say we cast just the value 0 to it, since we need something. And if we have the type, we can access a variable name. Sorry, it will be with an operator, and this will give us so we can get the address of this thing. And since we want to test what we are doing, let's quickly copy it here and fill it in properly. So type strings, we wanted var b, need a semicolon. What are we missing? So we get the address of var b, and then we just need to cast this to something like size t, and this will already work. So we're only missing size t here, and voila, we already get the offset. And as you see, the position of our var b is already at 8, not at 4, since there is some empty space, some padding injected by the compiler when laying out this structure. We can repeat this operation for the other arrays, sorry, all the other variables. So first of all, a, b, c, d, e, a, b, c, d, e, char-c, var-c, and let's see. So this starts at 0, so we can start another column, in the same column at 0. This, oops, we've already seen starts at 8. var-c starts at 16. That makes sense, since 8 plus 8 is 16. The next one starts at 18. At 18. So since this is only 1, there is already one thing inserted here. This will probably start at the right offset. 18. This is 2, so plus 2 is 20. and then we will have, so let's see, was 1 4, so we are having here 3, is this 3? Yeah, 1 2 3 4, yeah, 3 unused bytes of padding. So we have padding here, here and here, ensuring that whichever type we are using, the type itself is aligned to a reasonable boundary. So for example, our var_d is a short, so it will be aligned to a 16-bit boundary for better access. So we can also write down how our structure actually looks in a nice way. So 0 1 2 7. So we write down the 8 bytes for a 64-bit alignment, and then we can write down what we actually have. A goes goes until 4 ish. Then we have here some empty space. Then the next one, we have just our var_b. Then we have our var_c. That doesn't fit, so let's just write c. So doesn't fit. Then we have an empty. Just I don't know. Let's just leave empty. We don't have enough space to write it out nicely. Then we have two var_d. Okay, and then we have well, var_e, and the rest is empty. That's how our structure looks in memory. And the way this works, so we did here some assignments, but let's just do something with it. Just get the value and var_a1, var_a2. Actually, we can just go with var_a without a number. Just define it here. var_a3. Right. So we don't change what we have initialized here. So we just get values. So although we could also change this to use different variables. So let's go with p and c. Although this I would like to use as a demonstration that it really is p. Just go with p2 and then like this. Right here. So we have our structure, and now let's just see how this works in the assembly. So run it. We have here our this we don't need. So as you see here, it can use just one instruction to load the data that we have already seen before, that in an x86 instruction set, in a complex instruction set, you can do operations like this conveniently. And here we have our next breakpoint. Continue with the two different ways of accessing the variable b. and as you see, the generated code is exactly identical. So those two expressions are really fully equivalent. It is just a matter of what is more convenient to be used in a given point in time. Okay, so since we know that our variables, and before we continue, I will just show you one more thing. So here we have this locals view, or watch also works. So locals shows everything that's locally available, while watch we can tell it what we are interested in, like var s, and then just shows us var s and all its variables. It doesn't show, of course, the empty space which exists. If you want to inspect it, you can use the memory view. Let's move it here. Just specify an address or variable name, and as you can see, we have one. Then we have uninitialized memory, which when you have a debug build is being in fact initialized to a defined value, in this case CCC. Then we have the next variable 2, 3, 4, and 5, and the rest of the memory remains uninitialized. In the release build, this would just be 0, so it would contain garbage data. So what's important to know is that since everything is laid out in memory as defined by the structure and the compiler semantics, we can in fact access any of those variables entirely without really having awareness of this struct. So for example, if we know that variable d lives at offset 18, we can just take and let's go with short. No, let's go with this. So there is this type called size t, which is defined as a type def. Sometimes it's also defined with a preprocessor definition, and size t has the nice property, as I think I explained last time already, that it always has the bitness of the pointer length. So on 64-bit systems it is 64-bit, on 32-bit system it will be a 32-bit integer. So when you use size t for some sort of pointer arithmetics or something, then you can be quite sure that it will always be large enough to accommodate your data. So let's use this to access a variable. So we cast our address to size t. Then we know that variable d is plus 18, and then we know that this will be of type short asterisk, and we assign it 1, 2, 3. So now if we put a breakpoint here, we'll be seeing the value of which one here of our variable d has been set to 1, 2, 3. So this is something that in many other programming languages you could not do this explicitly, since such raw memory access is very error prone. More high-level programming languages try to prevent this, or rather they just either not allow it, or they have special language constructs that allow you to do such unsafe operations if needed. And this might be needed when you are interfacing with some C library or something like that. Although usually in almost all cases you would be able to somehow define a structure definition within your higher level language, and then have this mapped onto the C API, so that you don't really need to do such things manually. But it is important to know that you can if you need, and using this trick you could also in principle write something defined into this space here or wherever. So this, as I mentioned, there are no mechanisms in C or C++ that would prevent you from modifying memory any way you want to do. Any questions so far? Okay. So if there are no questions, then let's continue. So we have seen how this works. One thing I mentioned is that this padding, this can be changed with a preprocessor definition. What was it? I think it was pack1. And if we switch to pack1, then pragma pack1 was it like this? Yeah. So if we switch to pack1, basically it specifies the padding size that we want. Then it will not add any empty spaces, and then we see here that the size of this is just 16 bytes, as we would expect based on the fields we have put into. And this can of course then be also disabled. So if you specify this pragma pack, this will apply until the end of the file. So if you want to undo it, then you can use a pragma. You can just specify the right value. In this case, would be 8, I think. Yeah. Again, so you just specify pack1, and then you specify again pack8, and then it will behave as it behaved before. Okay. So let's continue. What you can also, of course, do is you can put structures inside other structures. So, but before we do this, we can also try to save on memory. Since we are here wasting all 8 bytes, we can try to just restructure our structure to not waste any memory. Let's call it 2. So the simplest way is just we put short here and the rest in the right order. And of course this goes away. Let's now measure the length of our structure. Files. And now it is 16. So the idea simply is that you manually move the elements such that they are properly aligned. This is not always possible. So if we would have, for example, if this would be, for example, a short, then we kind of couldn't really do it. We could, of course, move this one at the very end. So you can optimize, but you cannot necessarily always achieve the ideal packing if you still want to maintain memory alignment. But if you don't care for memory alignment and only care for the smallest possible file footprint, or you want it to not contain any invisible / hidden fields, then you can just use this pragma pack instruction to ensure that your data will be just packed as tightly as possible. And there are practical reasons why you might want this. So for one, this memory alignment is might to some extent also be platform specific. So there are scenarios where the system would maybe enforce less efficient packing, and then you of course might maybe don't want this. Or if you want to have a structure which you can move between different systems and always rely on it being the same, so that it is guaranteed never to change, then you would just specify which packing mechanism, which packing order you really want. Or if you are just sending data, so this would, for example, be the case when you are sending data over the network to another application, which might be written in another language running on another system, or if you are saving files which should be readable by various different applications. So in such cases, it is recommended to use this pack1, or you just define that, for example, everything needs to be 64-bit aligned. But usually for files or network or similar applications where you need some level of interoperability, it is really recommended to just use spec 1 and not have any hidden padding fields inside of your structures. Um, Next thing, of course, that one should take into account is that if you have the structures, that these names really, for the compiler, they have no meaning. If you change the order of two fields, then it will be just changed in memory. So if you, for example, would save, you have to define some structure, you have a program that uses this structure, and you are saving the structure to file. And then basically if you would want to change something in your program, like the order of those fields, even if you don't add or remove fields, just by changing the order, the old file you have saved will not longer be compatible. Because as said, the information about the name of the field is not preserved anywhere. The whole thing only operates with offsets, and that's it. So if you are saving things to file or communicating over network, it is recommended to always add some version information, which would allow you to at least detect if there is an incompatibility, or if you are loading some older file, then you could have like an older version of your structure, and then keep an older load function that would allow you to load the old data correctly. And then you would need some conversion function to convert it to your current internal representation. Generally, a typical approach nowadays is to not save raw structures to disk, or also often not communicate them over network directly, but use some more complex serialization scheme. So something where every field of your structure, or generally of your object, will get some unique identifier, be that either a full string as a name or just some, for example, 32-bit unique number. And then the data will be encoded with these identifiers, prefixed with these identifiers, such that if you add or remove fields, the loading function then will be able to properly handle it. This adds some overhead, or well, makes your files larger, but nowadays memory is reasonably cheap, especially in comparison to a few decades ago, where you really try to optimize memory usage or disk usage. Nowadays this really doesn't matter. If you can get more reliability by using a less efficient encoding, this usually is the more recommended way of doing things. But of course, internally within your application, that would be too wasteful, so there you would stick to using structures. And then of course, when you are working with libraries, you would also want to communicate with them just with memory structures. You wouldn't want to serialize data to some representation suitable for files and then communicate this to a library. That would be very inefficient. So let's continue with our structures. Let's see if there is anything else before we make things complicated that's worth mentioning. So yeah, I showed you can have a pointer to a structure. You can of course also grab a pointer to a variable inside the structure, just like this. And then of course, if you change the pointer, then you will be changing data inside the structure. So I think this already should be quite intuitive. Yeah. So the next thing will be to create a structure that contains another structure. So we can do such things. So let's call it struct my struct x, my structure extended basically. And let's grab the more efficient packing, struct2 stx. Then let's add another variable, int64 var f. Yeah, that sounds like a nice thingy. My struct x. var as, let's call it var as version 2. Yeah, and then of course if you want to set the fields, you can use the things, the operator to access things like this: 1 2 3 4 5 2 3 4 5 A B C D E, and F of course is then not on the SDX. Oops, that will be then the sixth one. Initializing like this would also work. 1 2 semicolon. So we can quickly check this, and voila, with 5. Yeah, that's the S6 and the one is 6. Yeah. So as you see, this actually kind of suppresses the internal structure. It just goes by the field order, ignoring the dummy field. So if we would use here just a struct, that would also work. Just that the whole thing would be slightly bigger. So it is intelligent enough to not try to set anything into a non-existing padding field. And what you also can of course do is, if you want to for example, you just want to add a variable and then you don't want to edit all your code and have to add this in between objects, so you could just call it struct links. You can just copy content of first struct and of the second thing. This is also B, wait, B, yeah, this is it. Snack. And let's of course you get maybe the size of this thing. Const int try version B. You can initialize it the same way. Let's go with PNP and we'll see that the sizes. So here we have 24 because this thing is 16, as you remember, it is more efficient, and then we added 8 and we have the right alignment, so we're not wasting memory. And this thing here will also be 64 because we just added something. And I'll just quickly write down the new, more efficient packing. So let's go for this one first. So we have var A, then we have var D. Then we have C and E. Yeah, that looks good enough. And this thingy, I know that could be longer, then let's keep it like this. C7, yeah. Now if we do this, then we just add var f, and this structure will just look exactly the same. And since they look the same, they can in principle sorry, they can in principle be used interchangeably. So we can initialize this here. We already did. So we have our var2 initialized with some values. This one here, let's just initialize with zeros. And then let's create a pointer var2x okay var sv2b and then we could assign this variable to it. Of course, the compiler will complain because it's not the right type, but we can just force the operation and then it works. And then if we run it, we will see here that it still shows us the right values from the different fields. So in memory, both of those structures look the same way, even though, of course, here the way they are structured is on the language level is of course different, since we don't have this intermediate structure. Okay, any questions so far? Okay, we have no questions, then let's see, did we forget anything? Nope, we have everything, so let's continue. So this structures allow you to create a set objects which contain multiple member variables, and they are stored one after the other in memory with some padding. And there is another thing in C and C++ which also kind of has members, but instead of using new memory for every member, it uses the same memory for all of them. So effectively, of course, at any point in time you can only use one of them meaningfully. So let's see, it's called a union, and let's give it a name, my union. And if we save some things, for example a int64 value, and then another int64 value too, and then let's create this value. So we assign value 1 like 1, and then we will see that value 2 is also 1. So as you see here, whatever happens, so if we then let's say value 2 is 2, put a breakpoint here, so we only have executed the first line. Let's add here value, and well, both are 1, and if we only execute the second line, both will become 2, because those two things, they have the exact same memory. That at this level sounds a bit useless, but you will see in a second why this actually can be quite useful. But just to hammer the point home, pv1, just really read the addresses. Runtime reference value 2. This needs to be, of course, value 2. So we have an address. Let's just have it output it and compare it. As you see, they are exactly identical. We'll also look in the disassembly to see that those two assignments also both look absolutely identical, except for a different value which is being here, except the different value being assigned, but it's still assigned to the exact same memory. And why this is actually quite a useful thing is because you can create more complex unions, and then this becomes useful. So for example, what you can do is we can add here a struct inside our union, and let's give it 32-bit values, int value low and int value high. And then you can use such a structure to split a number, a 64-bit number, into its lower value, so lower 32-bit and higher 32-bit, since this thing and this thing occupy the same memory. And this of course brings us to another interesting property of unions and instructions. As you see here, all three variables are shown semantically at the same level if you don't give this thing a name. If you give it a name, let's call it 10. Of course, you only have this part 32 and value, and then if you take part 32, then you can access those two. So depends on what you want. You would apply one of those two mechanisms to access the data. And now if we, let's say, value is equals 0x 1, 2, 3, 4, 5, 6, 7, 8, 6, 7, 8, F, we can just int L value punct value low value high. Let's run it, and voila. We need hex view, first portion and the lower portion. So this already is quite useful. To make it even more useful, let's create a slightly more complicated version of this whole thing. So union by union 2. Oops. Okay, and this thing will have char width 8 and struct part 16 containing short low low high high low, and you could also just created another array of 4 shorts, but I decided to do it this way, and then we can copy the whole thing and do the same thing just with 32. We of course only need half as much entries. High low, and then of course in 64 value, int 64 value and semicolon. So as you see, it already is getting more and more useful, and generally speaking, when implementing APIs or some low-level stuff, then you might have quite complex structures, and then what you might want to do, if you only have one function that you want to use for them, you would have a parameter which specifies which type of information you are passing through, and then you would just as an argument pass a union of different structs, which of those then is valid, and which of then that would be determined by your parameter. You could also do it more elaborate. You could start with a structure that contains a identifier, a type identifier, maybe additionally a size field to be on the safe side, and then it contains a union of your different potential types that you want to pass, and yeah, and then that's it. So this can be quite useful, and in fact such huge unions are used in the Windows kernel in various places when handling, for example, file information and other information types. There you have some parameter which identifies what information you just got, and then you can do something with it. Yeah. So any questions so far? Okay, no questions. Then let's first let's demonstrate that this thing actually works as expected. So union to value to punct value is equals, we grab this, and then we can also of course erase the portion to already see the reading. So path 32, oops, punct value high is equals 0, for example. You can do that, and then as you see here, we have wiped out half of the value. Here one of them is 0, and here of course two of them will be 0. So this works obviously as advertised. So let's see what else we can do nice with our unions. So in one of the earlier lectures, when we were handling just normal variables, you might remember that we've been using individual bits inside a, I think, 32-bit variable to basically as flags to indicate different states. And I showed you how you can set and clear those bits, which is reasonably easy, but of course not super pretty, since you need to type a bit more and use the right logical operators to only clear a single bit inside the variable. And C++, well, just C also gives you quite a nice mechanism how you can use individual bits of a variable without actually having to write all the boilerplate code to access this individual bit manually. So let's do that. So we create a union, my flag union, then we have a variable unsigned flags, for example, unsigned int flags. So this would basically be the variable that we had before, where we could read and set individual bits. But now, instead of reading them individually manually, basically with using logical operators, here we will make the compiler create the needed code for us. So we create a struct. Struct. We don't need to give it a name. So you might also have noticed that if we give a name to a structure, we then can create variables of its type. But if we put a structure inside another structure, we don't need to give it either a name for the structure itself, or naming even the member is optional. So here we create, of course, an unnamed structure, and int 32. So this thing is 32 bits. And now let's byte 1 is 8. So we are using this notation where we write a variable name and then double point, and then specify the amount of bits that it should use. And then this variable will be accessible as a normal full variable in C, but it will only use as many bits as we have allocated to it from the type which we are using. So byte 1, byte 2, also 8-bit, then nibble 5, 4 bits, oops, nibble 6, also 4 bits, and then we have, let's go with nibble 7, 4 bits, and then go with individual bits, bit 29, 1, 2, 3, 4, 9, 13, 31, and 32. And of course at the end we want a semicolon. In principle you can achieve the same thing. You don't need to like write it out after an int. You could also put an int an unsigned int before each of them individually, and the compiler will still just allocate single bits. But writing it like this is kind of more convenient, because you see implicitly how many bits you have left and to which memory block, to which integer this will belong to. So let's use our union. Var fu is equal. I forgot a semicolon here. And let's first see the size of it. Const int var foo size equals size of foo. So this thing is only 4 bytes, so basically just as big as this thingy. And of course, if you would have here entries of different sizes, the size of the union would be the size of the largest of its members, obviously. So for the others, it just adds padding in a way. Okay, so let's now use it. So we know its size. Flux is equals 0x 01 0f ab aa. So let's see. Let's see what this gives us. Var foo. Zack, and now we see basically the values for the individual values. So the whole thing, of course, contains the value as passed here. Byte 1 is just AA, byte 2 is AB, nibble 5 is F, nibble 6 is 0, nibble 7 is 1, and all those bits are set to 0. So if we want to set one of them to something, then let's go with F. And if we run this, now all of them but 1 is set. So if we want to only set the highest one, we can also go with 8. Then only the last one will be set to 1, while the rest will remain at 0. Voila. And then if you want, of course, to set any of those bits, let's see which one we want to change. Let's say bit 31, we want to set it to 1 as well. Yeah, and as simple as that we can. So now we see it has been set to 1. And if we would want to do the same thing using logical operations, go var foo flag. So this, let's comment this out. If you want to set it to 1, you want to set it. So I want to set it to 1. You can shift it by 30, I think, because here we have stuck like we were numerating them starting at 1, but of course internally they are numbered starting at 0. So here we need to shift this by 1 less. Let's see if we have done this right. Yes, we did. And we can of course uncomment this to compare the code that the compiler generates, how similar or how different it is. And here we have the simple way. So we load the thing, we set a bit, then we store it, and here basically do the exact same thing. So those two lines are absolutely equivalent, even though the first line is much more convenient to write and much less error prone, because you really have a nice name. Of course, you could create a preprocessor definition called bit 31, and then use this, and with the value at 30, and then use this here. But of course, this would be not as convenient. So the opposite operation, let's say we want to clear the last one. We want to clear 32 to 0. This is super trivial here, while here it gets even uglier, because we need to, so 32 1, we invert everything, and then we end it. Yeah, that should be fine. It should do the same thing. Again, we see the generated code is again the same, even though this definitely is much more convenient and much less error prone than this version. And of course, this works for accessing any of those variables that you have defined here on our struct. I see there is some question in the chat. Let's see. So there's a question for the structure syntax where you use it in the union struct part 16. Is the part 16 also just a name like struct? In the beginning of it there is a difference. So I'm not quite sure what the question means. So the name here which we provide is for this object. It is not a name for the structure itself. The structure remains nameless. And if we want to access those parts here, we'll be accessing part 16 or part 32. Let's say low, high. We are accessing it like this. If we would want to set the bytes, then we would go with struct to bytes. Bytes is an array, so we access it differently. It will reset high, so here we would probably want to clear 1 to 0. Now we would basically clear everything but the very lowest order bit. The structures here can get a name, like as part 32. Sorry, 16 of course. But it doesn't really influence anything. So this name only allows us to create something of this type further down. So if we would want to somehow access this thing, union as part 32 is equals. So for this we would need a name, but such a syntax here is already reserved for C++ only. In just C, you don't have like nested namings. So if you would want to do it, you would need to define. If you would want this to work in C, you would take the whole thing out of the struct, don't give it a name yet, and do it like this. Basically, what we did at the beginning here with our structure here. If you would be using C++, there would be another way to extend this to like this. But this is something that we will not be discussing today. This is something for C++. It's called inheritance. So we will just quickly undo all of those things. Leave this commented out. Yeah. Okay. Right. So here, as demonstrated, we can access all the different thingies. Yeah. So, any questions? Any more questions? Okay. So, if there are no more questions about structures, then we can proceed to the next thing. Depending on what we want, we would do either memory or functions. But since with memory we need to call functions, then I think functions is the more natural next subject. Yeah, I think this is complete. So let's create a new project. Create new project. Next. Oops. I just type it again to be on the safe side that it's typo free. So as you might remember, I already told you that this main function is in fact a function, and we have already taken a look in the stack trace to some functions that are called before our main function. So we kind of always already have had some interactions with functions, but we just ignored that and only handled the innards of what can happen inside the function. Now we will be really looking on how functions actually work. And the first thing, of course, to do will be to define our first function. And you first define, since normally a function has a return value, so mathematically a function is something that takes some arguments and returns your value, so it needs a return value. And some other languages are quite particular about it. So if you have some piece of code that does something and returns a value, then it's a function. And if it's a piece of code that does something and doesn't return a value, then it's called a subroutine. But in C and C++, there is no really a distinction between functions and subroutines. Basically, they are both the exact same thing. The main difference simply is that one can return a value and the other one does not use the opportunity to return a value, but on a machine level they are not different in any way and they could return a value in either case. And here basically in C and C++ you just, whether you return a value or not depends on the type that you specify. So a function that does not return a value, you just specify as type void. Then specify the name. In this case I selected the name my subroutine and my one. So any function in C++, first you specify the type, then you give it a name, and then you open brackets and start specifying arguments in whatever syntax, in whatever style you like. The arguments always start with a type and then the name, and the argument list is comma separated. And such a function cannot do really cannot return anything because the return type is void, which is a placeholder for a unspecified type. We already have encountered void when we were playing with pointers. So there, a void asterisk is a stand-in for any type. It is a pointer to something. And unlike normal pointers, you cannot do pointer arithmetics with a void pointer, since the void pointer doesn't know how large its individual unit of allocation is. But if you want to actually create a function, not a subroutine, you pretty much do the same. You just specify a valid return type, like for example integer. And of course, let's call it my function. And of course, you cannot create two functions of the exact same name if they are not differing in something else. So in C++, what you can do is you can in fact have multiple functions with the same name as long as they differ in the argument list. And then the compiler, based on the arguments you specify, can intelligently find, or maybe not very intelligently, but just algorithmically find out which function actually matches and then use the right one. So this might be quite convenient in some scenarios. You don't need to invent new names for the same function if it just does the same thing, just with different arguments. So this is quite convenient in just C. This does not work that way. The main reason is that C also is less strictly typed than C++. So C++ does not allow you to cast from one pointer type to another pointer type implicitly. You need to explicitly specify that it should use the other type, indicating that you know what you are doing. While in C you can often just assign a pointer of one type to a pointer of another type, and it will do it without even throwing a warning. So of course, when we would want to use types to identify which function to use, this less strict typing would be in the way. So this functionality only works in C++. For all practical reasons, since we are using CPP files here, we can use everything that C++ is capable of inside our files, even though currently we are still restricting ourselves to use only the C portion of the language. Okay, so let's make the function do something. So for example, define a local variable which only exists within this function, my result, which will be just the sum of those two thingies. Boring, but good enough. And if we want to return a value, we use the return keyword. And return, of course in data function you cannot return anything, so you just return. But you don't need just to return. The whole idea is that when you call a function from somewhere, then the function starts executing code, and then you can return to the place from where your function has been invoked using the return keyword. And you can either just return, or you can return and then returning a value. So if you have a function that takes that returns something, you always need to return then this something. This must be, you cannot just return like this. This will be, it will be complaining if you try to compile this, or at least it should be. Yeah, it must return a value. And of course, if you would try to return something here, it would also complain that this function cannot return anything. And also the thing that you are returning must be somewhat compatible. So of course, int and int that's the same type, that works perfectly. But if you would have like a int int64, for example, that would also be fine. Depending on your settings, it might or might not throw a warning, as it did here. So it tells you that you are returning something that is bigger to a smaller type, meaning that the upper order bits might be truncated. I mean, they always will be truncated, but often, if you, for example, just add 1 and 2, then you won't use the upper order bits anyways. Only if you add 2 billion to 1 billion, then you will end up with close to 0 or 0, depending on the exact value, because everything past 2 billion will be cut off if you are using a 32-bit number. So those things one needs to keep in mind. Okay, so since we have our first function, then let's use it. So let's define some arguments. My arg1 is equals 1. They don't need the same names, and maybe to demonstrate, I should really call them differently. Let's go with my var1. It will have some symmetry indicating what is what, but it will be explicitly. But I can at least remain at the same coding style. Okay. So if you want to call and then of course we need a variable one to get the return value. So if you want to just call a subroutine or a function and you don't care for the return value, you just write its name, then you open brackets, and then you provide the required arguments. And if you care for the return value, or if you have, then of course it needs to be a function. If you would try to write something like this, the compiler would complain because void is not valid. So you need something that has the right type. And voila. So at this point it really looks like just in math, where you just write a function of something and then it does something internally and returns your value. And this kind of is how first programming languages started. So computers were tools to do well, computing calculations. Just this nice note on the side. If you listen to some older sources or read older sources, then they will always be speaking about electronic computers. And it kind of, from the modern standpoint, is that of course it's electronic. What else could it be? Well, first of all, it could be mechanical. They were designs for machines that could compute values, and they just needed to be cranked on the side. So non-electronical. But in fact, a computer was a job description for a person who was working for scientists and just doing the computations for them. So scientists wrote down some equations and then gave it to their computer, and that person had to do the computation basically by hand, or using simple analog helper tools like logarithmic tables and rulers and stuff like that. And thus, when they invented electronical computers, it was fancy new because it was electronical. It was much faster and, in fact, also very quickly much cheaper than employing people to do this by hand. So this just as much on a small tangent. And then, of course, programming languages became more and more complex, and its origins in mathematics are not longer that apparent. Okay, so let's put a breakpoint here, and before we start this, we will have to set a few configuration options because modern um, modern compilers create a lot of additional code which is just unnecessary if you want to just see the very basics. So let's switch this to all platforms, and this can be, let's just leave this at debug. So this we don't need, nope. This we, I think, can also turn off. Code generation, basic runtimes checks, we don't want this either. Security checks, no. Okay, I think this should be fine. Let's build it. Yeah. Okay, and let's run it. So we are here in our main function. As you remember, in the stack trace we have another main function and yet another main function and some in between functions, and then some functions of Windows itself. So there is already a lot of stuff happening before our application's entry point gets triggered. But as soon as, well, we are in our entry point in our function, then our own functions will be called. And what we see here is that we have our two variables. So one lives in well, RBP plus 0, and the other one lives in RBP plus 4, but it doesn't show this to us so nicely. So yeah, let's disable this option, and we see the memory location of our two variables. As said, the first variable is just at the beginning of our stack frame, and the stack frame is pointed to by the base pointer BP register. And then the next variable is of course then just plus 4, and then of course the return value will be plus 8. So we already have here, so we load those two variables into registers ECX and EDX. These are two registers which live here, so we can step through this, although we won't see anything since they already have these values from the previous operation. This thing did the same thing already. But we just step through it. Only see in the instruction pointer being being incremented, since the other does coincidentally already had the same values. And then we have here this call instruction. This instruction can contain various formats. So it can be an absolute call, so you can call to an absolute address, or you can call to relatively, so to something that is just relative to where you are right now. And in this case, since this thing is only 4 characters long, 5 characters long, and an address of course would be 64-bit, so it would be much bigger. We see that this usually is just a relative jump instruction, well, relative call instruction. So let's execute it. Zack. And yeah, I didn't disable one of the things that I needed to disable. Income, what was that? So the thing is creating for all function calls redirection tables. That might be it. Let's see. Nope. I mean, we could just ignore this. I think the linker is what's doing it. Link. this was it. No. Okay. I think. Okay, so we set the two registers, then recall. We can observe what happens here. So, of course, whenever we execute any instruction, the instruction pointer is incremented. Another thing about those registers, as I already said, there are actually it now changed quite a few things, because it's also not using RBP, but now it's using the RSP register. So let's quickly just undo the other thing, but I think the other thing will be of no consequence. Where was it? Yeah, this one we have changed, but this thing I think won't matter. I think just the fact that we disable the incremental linkage, that is what changed which register it's using. Okay. No? The other thing actually was the other thing. So generally there are two registers which are related to the stack. So our memory that the function is using, the base pointer and the stack pointer. And this base pointer is a register which, if you want to have a nice code which is nicely debuggable, you should be using, or rather you should set the compiler to use it. But if you want to optimize and have as optimal code as possible, then usually the compiler would actually just reuse the RBP register for other things, just as it would just use it as a general purpose register, and use the RSP, the stack pointer register, for everything. So just to clarify, as we have learned with pointers, you have pointers that point to something, and these functions, of course, if they are doing something and have local variables, they need to have some memory, obviously, be able to somehow systematically access new memory, and this is done using this stack pointer. So you have basically, when you start a thread, so an execution of code on your modern system, there will be some memory allocated for this thread automatically by the operating system, and the address to this memory will be set into the RSP register, and then the code will start execution. And inside this RSP register, you can increment or decrement it, and then walk this amount of memory that the operating system has allocated to you. There is some trickery with regard to memory efficiency. So generally, when you create a thread, you can either tell the operating system to just create a memory region of a default size, or you can specify how much memory do you want to reserve for the stack. But the way internally this works is that usually the whole memory will not be committed instantly. So we will take a look into this later, but here it's just important to note that this RSP is the pointer, basically, which tells the whole function where its own memory range starts. And since the function doesn't know from where it will be called, the function cannot rely on any static addresses normally. So it will rely on this stack pointer to set up all its memory when it does something. Okay, so let's continue. So we set those two things, then we do the call. And what we notice here is that not just the instruction pointer changed, but also the stack pointer has changed. And the reason for this is that a call instruction, unlike a jump instruction, saves the address plus its own length from where it was called onto the stack. So if we rerun this code again, we make one step. Oops, that was too much. It's always important to click into this window, otherwise this instructions here do two steps. So we have our stack pointer. We'll open a memory window. We already have a memory window. Let's move it here. Zack. Okay, so this here is where the stack pointer is pointing to. Then we execute the call instruction. And it didn't change at all. it changed, but it didn't show it. Can we make this better? No, not really. So the thing is, if there is already something in memory, then of course it does not show you that something changed. Let's go again. So register. So this thing points here. If we now do one step, it should in principle write the address. Okay, it changed something. It changed here 2 bytes. I said there was already something close to the right value before. You know what? Let's disable this subroutine because it just makes tracing what's happening much more painful. So let's just start all over. Let's go to our registers now. RTX and RCX just contain. RCX contains something, but RTX contains completely garbage. So one step, 2 step. This one I said was the same. So, but at least we see that this one was changed. And now, if we go to the stack pointer location, memory, then now it contains all zeros. So the thing is, normally when you have an array or some memory, you start at an address, and then you work your way towards higher addresses. With the stack, it is usually the opposite way around. So you get some address, and then when you operate, you start going to lower addresses. So your stack grows in the other direction. So here we have the call. But before we do this, let's here also write down RSP, the value of RSP. We do one step, and as you see here, it wrote a memory address into the location, and RSP was decremented by 8. So it does 3 things. It jumps to the location that is specified. The call instruction jumps to the location that it's supposed to jump, like a jump instruction. But then it does 2 more things. It writes the address, the return address, so the next address after itself, into the position the stack is currently, the stack pointer is currently pointing to, and then it decrements the stack pointer to the next free slot, so to say. Yeah. So and this information is very important because from the function we want to be able to return to from where we called the function, and this return address which is saved on the stack is the means by which we achieved it. So when this return instruction here, this return keyword which translates to a return instruction, is invoked, then what it does is it reads the value from the stack and then it jumps to it. So in principle, one could say that at this point you could also just read the value from the stack to the register with one operation, and then just make a jump instruction to your register value. But of course here, if you have a dedicated function to do, dedicated opcode to do this, this is of course a bit more efficient. And in fact, in modern systems, this is actually required. So there are mechanisms to ensure that when a function returns, it can only return to the address from which it was really called. This is quite new. Usually in the past, such things were not enforced, and thus people that found some exploits allowing you to write memory usually tried to just get your application to start executing a long chain of partially complete return instructions with some opcodes before, and then with the right mechanism, right trickery, you could really write basically arbitrary programs that then only operated based on this returns and the few instructions that were before. So this is called return-oriented programming, and it's a method of injecting exploits into systems. And since this was such a effective and popular method, modern systems maintain a shadow stack, and then if something happens that overrides the return addresses, when a return instruction is invoked, and then it tries to return to a position not from where it really was called, then the CPU will backcheck. Of course, this consumes more memory, but this is security-wise quite an important improvement. But here we don't have such mitigations enabled, so if we want, we could do quite a lot of dirty hackery with return addresses and stuff like that. Okay, so as said, we have jumped to the begin of our function, and as you see here, the function does a few things. So first of all, it saves the two registers into memory at defined addresses based relative to the stack pointer. Then it uses a push instruction, which basically is just get the value from, in this case, RBP, put it onto the stack, and then advance the stack to the next slot. And the idea generally, since those registers are the same for all the functions, is that if you call a function, then some registers are defined as volatile, meaning that if you have been using those registers in your code and then you call a function, when the function returns, you cannot rely on the content of those registers remaining unchanged. Basically, since they are volatile, a function can use them, it can override them, and it doesn't need to restore them to their original values when it is returning. Another set of registers are in fact defined as non-volatile. Of course, this is just a convention, so there is nothing in the hardware that would enforce this either way. It is just about the compiler behaving as the convention, the calling convention specifies. So the other registers, so for example, RCX, RDX are volatile registers. After you call a function, you do not expect them to remain the same. But for example, RBP is a non-volatile register, so if you call a function and your function internally wants to use this register, it must restore it to its original value before it returns. And the typical mechanism of doing this restoration is to first just push it on the stack, and then before it returns, using the pop instruction, to just read the value back from the stack to the RBP or whatever register, or whatever non-volatile register you have that you want to return to. So here, since we want to use RBP, we have to save its content first. Then our function will need some of memory of its own, so it decrements the stack pointer by 50h is, I don't know, 80 characters, 80 bytes. So now our function has 80 bytes to work with. Of course, this is much more than it's needed to do this operation, but well, that is how much the compiler decided to allocate. And then we can move the current stack pointer to RBP, and then do all our operations here using RBP. So we can read again those things back. Since I said it is a debug compile, it does not optimize, it just does things one by one. So first it was saving registers to memory, and now it's reading them from memory, just that back again, even into the same registers, although it might have changed their order. One thing you might notice is that it is reading them relatively to the registers, to different registers, but mathematically at this point in time this value will be equivalent to, I guess, this value. Yeah, it's a smaller one. Then it does the add operation. Well, we have the result then in ECX, and then it saves it to EAX, since EAX usually is used for return, but in this case it just does it so it can save it to memory. The whole function, our simple function here, could be much simpler. It would just need to add RCX to RDX and save the value into EAX, and then already it could return. But as said, it's a debug build, so it saves everything to memory additionally, even if it's not needed. So here at this point, this instruction here is completed, and then we have our return. And what this thing does is it first loads the return value into the EAX. The calling convention for x86 is that return values will always be returned in the EAX register, and so this it needs to be saved there. Of course, you could have a different calling convention. This is not something again that is enforced like hardware-wise. That would be like in the CPU specification. You can, in principle, define it differently for your compiler, but then of course your compiler will no longer be compatible with any other library, which would be of little utility. But to some extent, this is something that you might encounter. So these different behaviors, especially with regard to the cleanup behavior on 32-bit Windows systems. But this we will take a look into a bit later. For now, we are just looking into the x64 calling convention, which is just a simplified calling mechanism. And while in the 32-bit Windows system you had like 4 different calling conventions, on ARM you only have one calling convention, and on x64 you also have only one calling convention which is used. Yeah, so we load this value basically again, and then we here need to restore everything. So we need to restore the stack pointer, we need to pop RBP back, and then the ret instruction will read the address from the stack, increment the stack, so we move one entry, and then jump to the next instruction in the code. So the first instruction that is after our jump instruction. So let's make a step here for everything. Step, step, step. Okay, here we prepare our return value. You can already see our return value here in the RAX register. Then we restore the things, and as soon as we do return, we end up at the next instruction after our call. And here we just take the value from EAX and save it to the position of our my return value 1, and that completes our function call. Now you might of course wonder since you certainly noticed that our count of registers is limited. We have like 16-ish registers, and at least on x64, and some of the registers have special meanings, so the amount of registers available for arguments is kind of limited, obviously. But normally when you write applications, write applications, then normally you are not really constrained by the amount of arguments that you can pass to a function. In fact, the Windows API contains quite many functions which has a dozen of arguments or more. So how does this work? Well, let's just try it out. Let's just make a function which has 10 arguments, which is much more than could be passed in registers directly, at least on our platform. ARM has more registers. ARM has like 32 registers, and like only a handful of them have special meanings, so most of them can really be used for whatever. But then of course you still would be limited, and you still might want to be able to use even more arguments. You might have a function of 24 arguments or 100 arguments. So at some point the compiler might say, oh, it's not capable of handling that many, but it's not a fundamental limitation. It would be just a implementation limitation of the particular compiler. So when you create, for example, structures and create member variables for inside of structures, there also kind of is no limit. But if you go past a few hundred, then the compilers might start to bug out with some errors that they cannot handle so many members. But this is then something that in principle could be fixed on the compiler side. It's not within the language definition said that this is like there is a hard limit of so and so many. Okay, but here let's continue. We now I don't think it's 10, but we first need to change the names so that they don't conflict with each other. And we are too short. 9 and 10. And in principle we could return like a sum of all of them. Why not? 2, 3, 4, 5, 6, 7, 8, 9, 10. 3, 4, 5, 6, 7, 8, 9, 10. Yeah, and let's call it. Again, let's just comment this out so that we see really what's happening. 2, 3, 4, 5, 6, 7, 8, 9, 10. 3, 4, 5. Wait. Oh, I don't have these variables. Then let's just 1, 2. So of course you can use variables as arguments. You can use literals as arguments. Is it complaining? Why is it complaining? 1, 2. Shouldn't be complaining unless I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Should be fine. Oh, sure. I also need to call the right function. Right, so you can use literals, you can use variables, you can use const variables, and of course you could write a whole equation as an argument. So you could write like 2 plus 3 plus 5, also fine, or plus 1 plus 2 times 2, whatever. So you could also call another function from within your function here. So it's really very very flexible, but for simplicity now let's just stick to 10 and let's run it. So, and here already we see that we don't use so many registers as we might have available. So as you might remember, we have like 8 somewhat general purpose registers from the 32-bit era, and then we have another 8 registers introduced in the x64 extension. So it starts with R8 until R15, and then we have the future special registers like REP and so on. But as we see here, for our function call, we are only using 4 registers. So the arguments we also see are kind of saved back to front. So first, second, third, and fourth arguments are passed in the x64 calling convention within those registers. This is defined in the standard. In principle, you could write your own compiler that handles it differently, but that's how any modern compiler does it. And the rest of the arguments, so our 5th, 6th, 7th, until our 10th, and however many more there might be arguments, they are just written to the stack directly, and the function then is supposed to just look at them up at the stack, since the stack pointer is something the function can refer to. And once it was called, of course, the stack pointer will change, but it changes in a defined way. So the function knows at its beginning the stack pointer now points to the next empty entry after the return value, and before that there will be those things saved. And the way this is done here on the Windows calling convention, at least, is that the memory regions for those values here, as you see, we started RSP and we kind of also growing here, but here this RSP does not reaches like RSP plus 0, but in fact we only have plus 20. So this let's copy this maybe, but with a few changes. So we don't want the addresses and we don't want the code bytes, we only want this. So if I can switch back, let's put it here. Let's make this a multi-line comment. Right, so here kind of RSP plus 18 hex, 10 hex, 8 hex, and 0 remain unused. Okay, so let's go, and here of course this would be the name of our function. Right, so let's continue. So we are writing those things here to this. Yeah, let's restart it. Rebuild and apply. Even if you just change comments, it considers it a change and wants everything to be recompiled. Right, so we are at our call. So we do our jump. And what we see here, what happens is the first thing the function does is it will save. So first of all, RSP has changed in the meantime because we put the return address onto it. So now of course the offsets are shifted by 8. So this plus 20 in fact is just plus 18 with regard to the old value. So what it basically is doing, the function here, it takes all the arguments, the first 4, that was passed into registers and writes them into memory into this location. So maybe I could let's leave it like this. Which might look strange, but we'll learn later why this is quite a useful mechanism. Of course, if you would have an optimized function, then it might just use the registers directly and not save it back to memory or anything like that. But if you have a debug built with all the bells and whistles, then this is how it behaves. So it first of all saves back those data, and then it saves again the base pointer. It reserves 80 bytes for itself. If the function would of course be longer, then it would reserve much more bytes. Why it reserves all 80 bytes while it only needs well, it also reserved 80 with a much simpler function where it only needed how many? 24, no less. It only needed wait, for 12. It would have only needed 12 bytes, but it reserved more. And currently the way the compiler does this is always it reserves always as at least 80 bytes, which again is kind of wasteful. We could later take a look how this would look if we have the optimizations enabled, then it should be much less wasteful. Okay, so it does its thing, then of course here it performs the operation. It just moves a few data around and then just adds into a accumulator register until it has done all the adding. And to do this, it's just using here this RBP plus an offset. So technically, it is reaching into the memory that belongs to its caller to access those arguments. But this is fine. So it does this. It saves the value into its own memory. Then it reads it back. So these two operations could be just left out. They don't change really anything. Then it of course restores everything, and then it returns, and the value, as we remember, is stored in EAX, which then is just saved to our memory, which is reserved for the return value. So any questions? Okay. If there are no questions, then let's continue. So we have seen how this whole thing works, and what we can do now is to see how it would behave if we, for example, have a structure as an argument. So with the higher arguments, it's kind of more intuitive how a structure would be handled, but for the first 4 arguments, of course, it kind of seems strange because you cannot fit a structure into into a register. So let's see. Let's create a structure. My struct int var1. We will now, just for simplicity, keep all the types the same. 2, 3, 4, 5. And the first simple case is a function which just takes a further argument of a particular type. Of course, one thing that I guess is intuitive, you could just use a pointer. And then this thing fits into a register, so it's perfectly fine. So it's a boring case. We won't look into it yet. We will first start with the normal case. So we have a structure which we want to pass here as a copy. So the important thing, by the way, is that if we change those values here inside, this will not make any changes outside our function. So a function normally is getting the arguments by value, so it can do with the value whatever it wants. Of course, if you have a pointer, then while changing the value of the pointer won't be pointless. If you change the value of the thing the pointer points to, that will have an effect outside the function, obviously. So let's make this do something. Yeah, let's just plus struct var3. Good enough. So we need, of course, a struct my var_s. 1, 2, 3, 4, 5. Then we just call our function my var_s. That is function. Let's just call it function s. We don't need to type so much. Okay, so breakpoint, run. Okay, so as you might remember, normally we would be using RCX, RDX, R8 and R9. But here we see that while well, actually quite a few things happen. So first of all, we load an address of RBP plus 70. I guess this will be unused memory. So we have some additional memory, of course, in our stack, which we have not yet committed to anything. So this will be RBP plus 70. Into the other register RCX, reload RBP plus 8, which now is our... Actually, we should not change the values because this changes these values here. We don't want it. Let's rerun it. Then it will not be plus 8 but plus 10. So we show names. Yeah. And of course the empty thing doesn't change. So here we have unused memory. Here we have memory that we have that contains our structure. And then we copy into RDI and RSI those two values. So again, we could have here loaded those directly into, why the compiler does this in multiple steps, I don't know. And then we specify something to ECX, and 14H is in hex 20, and I think this thing, yeah, this thing is 20. So it already looks kind of suspicious. So let's see how it continues. So we have here the address of the address of where we want to copy our structure to, the address from where our structure lives, and the size of our structure. And then we have here this rep moves, and this is a way that in the x86 architecture you can implement a loop in the absolutely least complex way possible, because this rep prefix to move s will repeat move s the amount of times written in ECX, and each time it does a repetition, ECX will be decremented by 1. And each time it does this, what it does is it takes a byte from the RDI register, from the memory pointed to by the RDI register, sorry, the opposite, the way around. D is like for destination. It takes a byte from the memory pointed to by the RSI, so source register, and then puts this byte into the RDI register. Of course, this could be more improved. It should not operate with single bytes. It could operate with words or Q words even. Then of course just this would not be move S, but then move D or move Q or something like that. And of course RCX would be smaller. But let's step through it. And then I changed something. I wrote 20 there. Let's restart it again. Yeah, so we are where we were. And of course, if you don't click into the assembly, your steps the whole line, which we don't want to step here. And then we step, and when we step here, we are kind of stuck, but we see here that things are changing. So RCX is decrementing, and RSI and RDI are being incremented. So we just step until the thing reaches 0. And then when it reaches 0, we are done with our micro loop, so to say. So what basically happened is that the caller function has created a copy for the call function of this structure, and it will pass to this function which takes a structure. It will pass only the address of this copy it created for it. So here, and we in fact are using even the right register. So as you see here, we are loading the address into R8. This is basically the address of where our copy lives. And if we would have, of course, put our structure as the 5th or 6th argument, then what would happen, of course, is that it would have just put it here or here, this address. Okay, so it does this. Then it sets RCX and RDX as expected, and then calls our function. And now, of course, inside our function, the whole thing does the same thing. It saves the registers back to where it has room for them before its own space. The idea here, I will explain this later because there are two ideas and we don't want to confuse them. So let's continue. It saves the things, it saves the stack state, it does its operations, and then it just returns as we have seen before. So we don't need to step through this since it's quite similar. We only have one more add, which then just reads from the RBP plus the right offset. Let's see if we get symbols. Yeah, so this line reads from the struct, which is an RBP plus 70. And then of course we return. The same thing of course we can do with a return argument, but before we come to return argument, let's see how else we can pass an argument. So we already have passed it by value. Then of course the other way of passing an argument, any argument, we could also do it with the ins is as a pointer. But here let's do it directly. So we need to change this like this. And let's call it. This thing will of course want us to make this into a point, so we need to get the address. Let's leave this here. Okay, so we see here of course the calling is much simpler. We don't make a copy. We can skip all the code here. We just load the address where our struct lives, which we remember is RBP plus 10, as we see here, into R8 and the other two registers, and then we just do this whatever we do. So for what the function internally is, for what the function itself cares, actually they can we quickly jump to them? Yeah, kind of. What it does internally is very similar in both cases, because in both cases the function really just gets an address to a memory which it can use. So whether we pass a structure by value or by pointer, the function on a machine level, the resulting function on the machine level looks exactly the same. The only difference is what it gets as an input. And as you might remember in C++, we can also pass something by reference. So we just so that's reference. And this functionally is the same as passing it by pointer, just with the only useful difference that you don't need to use the arrow operator. Instead, you are using the dot operator, and it's kind of an implicit pointer, a hidden pointer, one could say. So let's call this R, like reference. And here with R, we will see that the last two function calls look absolutely identical. So it really is the exact same thing. And all our three functions, in fact, would be binary identical as well. Okay, any questions? Any comments? Okay, so if there are none, we still have about 10 minutes left. So we will not finish functions today, not fully, but we can at least take a look on a few more nice things. So obviously, how do we return a structure? Because this also is something we might want. Zack. Well, one obvious thing, of course, how we can return a structure is if we do this, then we have a pointer and we can just write to it whatever we want, and this way we can return a structure. Duh. So this is kind of a obvious, simple way of returning a structure. SR, and here we want to make a structure. My struct. We initialize everything with zeros, as you remember. Oops. My struct. If we just write one thing, the rest of the structure will be padded with zeros for us, so this is quite nice. Let's say we want to return as var1, and this thing will return the whole structure. So let's see how this works. Those we can comment out. My var s is equals, this was sr. My naming is kind of boring, but well, why not? So let's see what happens. So we didn't change anything else. Still s. So we see there are a few things which changed. First of all, we notice that we are no longer loading. Actually, I should leave something here so that we can compare it to. So basically, on the C level, we have the same. We have a function that takes the same arguments, just that this one returns a integer and this one returns a structure. And the one which we have here is quite simple: ECX, EDX, call, return, done. While here we see that the same values, the same positions, those two, are written to different registers. The whole register usage scheme has been shifted by one register. Instead of using ECX and EDX, and then R8, R9 for the other two, if we would have more arguments, we use EDX and R8, and ECX will be used for, and ECX is filled with the address of of a memory block which is not yet used. So RBP plus 80, it doesn't have a name or anything. So we are giving the function a memory block to which it can write, which is fully uninitialized. So if the function would just just execute the return opcode, you would just have garbage in our return structure. So let's see. We have those things, then we just do the call. So let's do it. Zack, 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 zack. And now we are inside our function. Again, we save our argument registers. We save the stack. Here we use this rep trick to initialize everything with zeros. We pretty much make EAX 0. We set the size, and store, I think we'll just take whatever is in EAX and store it to RDI, to our destination register. and this whole operation is repeated and RDI is incremented, while of course EAX just remains as is. And here it uses also a store which just stores a byte, so it's not super efficient. A release build would probably use a different operation, which would work in 64-bit or 32-bit chunks. Then we of course do our normal additive operations, but we save the result somewhere else. We save it to where the RCX register points. In the RCX register, it contained the pointer of our a pointer pointing to our free block of memory. It was saved to some memory, then it was loaded from the same memory again, and then so we end up with the same value in RCX, which is important because in the meantime we have used ECX for this rep opcode, rep prefix, and this rep prefix requires the use of ECX, RDX, RSI, RDI and RSI. It does not operate with other registers. So while the registers generally can be used as general purpose registers, they have some additional special function. And C is like a counter from its name, so that's why it was chosen for such thingies. And RDI and RSI were introduced later. Yeah. Right. So we are just saving our basically we are just saving our return value here somewhere else, and then we just again clean up the stack and return. So this is how structures can be returned. We just shift the whole register pattern and pass an address to where the result should be written to, and then of course here we load the address of the thing we had before. We prepare everything for rep, and we do this rep moves to then copy into our struct s. At this point, one could of course think that we could just pass to the function the register of myvar s directly. So the function would just directly write it in there, but the way it is defined in the standard is that you give the function a new memory and then you copy the things using your assignment operator. And while here on the level of just C and just simple structures, this sounds wasteful. Once we will start using C++, we will see that there actually is a good reason why it is done exactly this way and not any other way. Right, so we have here apparently we copied then everything twice, so this might actually be a bit too wasteful in the debug bit, because apparently I said we are copying it not just once but twice, and this is once too much. We don't really need to move it around so many times. But the debug build is not supposed to be efficient, it's supposed to be good to debug, and the more copies and redundancy you have, the easier it is to debug things. Right, and with this we ran out of time, so there will be no homework. Though I could, with what you already know, I could give at least some simple homework. Let's see. So you can write functions with a fixed amount of arguments. Yeah, this is, I think, simple enough. So homework from the 16.04.2026. Write a function void set flag interfind flags, comma int of set int value. Let's go. Let's call it setBit. So you have a function setBit which takes a reference to an integer which contains flags. It takes an argument of offset and it takes a value, and this can be true or false, and this thing should set this one bit inside of your flags, a variable which has been passed to it. You know what, let's make it a bit more complicated. Let's make this a pointer, and flags flag size. So you get a pointer to a flags variable, flag size in bytes, and the size. So you could, of course, when you call it, you could of course use the size of, and this could be either just an int or an array of ints, and then you can set at any given offset. So this offset is not limited to be 32-bit. This offset can be more, which then just means that you need to go to the next integer in your array, if this is an array. And let's make a different return value. Let's have a return value of boolean, so that if you would specify an invalid offset, it would return false. And then it is supposed to change one bit to true or false. So I should actually write this down. The function takes a pointer to an int or an array of ints, int32s or an int32, and a size of the integers of 2 data, comma, and int32 and bites, an offset of a bit to set in bits, offset in bits, starting at 0, and a value the selected bit to set true like 1 or false equals 0. False if the set was of the bounds of the forbidden data. Yeah, I think this is a simple enough homework assignment. You already know how to use pointers and how to access things in arrays and ifs and loops and whatnot. And I think this is quite a funny function. You can in principle try to use some trickery to simplify the work, or you could just do it fully manually. There are many ways how this can be made. Of course, you should provide some test cases. So and there was a question via email this week about what exactly to upload to Moodle when you upload your homework. Just you can see on my uploads what you need. So basically, we can do this here. So since we have written everything down, struct we can close. Let's go to our struct. So you just select the SLN or SLNX file in the folder containing your source code, and then you zip it, and then you open it, and inside you have this x64 folder which contains debug and then some intermediate files. The whole thing can go away. Yeah, Windows is kind of bugged, but it still removed it. So now it's only 4 kilobytes, so it's super small, and it only contains a SLN file, a few project files, and your source files. and this is what you should upload to Moodle each time. We don't need all those temporary or intermediate files. Well, if you upload the make file, then you're not using Visual Studio. I will find a way to make it work, so this is fine. I just wanted to emphasize not to upload all this intermediate compile output stuff because this is just a waste of memory. Okay, I guess that's that. If you have any other questions, I mean, you can ask them now, or you can email me your questions later. And we will see each other next week. And let's stop the screen sharing. But before you go, there will be a small announcement with regard to the timings of the lectures. I think the over next lecture was the Freigabe. Was the screen sharing not working? Well, the recording will be uploaded to the Moodle anyways. No, here is the screen sharing. Freigabe stoppen. Right. The announcement. The lecture in the week after the next week, so on the 30th of April, will be at 10 o'clock and not at 15 o'clock. So I hope you can accommodate it in your schedule. If you cannot, then you can also, of course, watch the recording later on. This is fine, but just so that you know, I would be happy if at least someone comes on the earlier hour. And that's that. I will repeat the announcement in the next lecture anyway, so that no one misses it. And I will, if I don't forget, also send out an email with this time shift. Yeah, and I think that's that. Stop the recording, and we will see each other.